So let's take a look today at problem solving. And here's what I'm going to suggest as well. Get comfy, put your feet up, face the screen so you can see and be ready to interact with this as I discuss it. Be ready, put your feet up and get ready. Okay, so I know it's no big revelation to you guys that problems have always existed. And generally, when you solve problems, you don't need a computer to solve every problem that comes in front of you. The computer is a tool, as we've talked about yesterday. But it's a useful tool for some types of problem solving. It makes it more efficient. Oops. So as a tool, we want to use the computer to solve these problems. But before we do, let's take a look at problems themselves. And one way we could classify problems. So for example, we could say, this is a hard problem. This is an easy problem. This is a problem that I might need math to solve, and this is one that I don't need math to solve. There are lots of ways you could classify problems. But one way you could classify them is according to their solutions. So I'm going to present 4 ways to do that. Okay? Type or classify the problems based on solutions. So the first type would be problems that have a well-defined solution. Simple example would be 2 plus 2. Very straightforward solution. Or how do I bake a cake? The solution to that would be follow a recipe, right? You're going to get a cake. It's not like there's a lot of ambiguity there. It's a well-defined solution there. Second type of problem would be lots of solutions. An example of this type of problem would be when you guys hang out tonight is what should we do tonight, right? There's lots of possible solutions to what should we do tonight, right? If it's Friday night. Let me give you, I'm kind of like predicting what your average teenager at your age would do on, say, a Friday night. So here's possible solutions, right? Homework, right? That'd probably be number 1, right? Go to the library. I know that's super popular Friday night. I see you guys there so often. Go fishing, right? Oh, that's maybe a little cold. Watch TV. Come visit Mr. Walks at his house. Sure, why not? Come on over. You can take care of my cat because it's driving me nuts. So that's many solutions. Third type would be what's called the optimal solution. So in this scenario, you have lots of solutions, but one of them might be better than the others, or optimal. So let's say you worked at a factory, and they said, look, we need you to design a container to hold apple juice, but tin is really expensive. So we need you to design a can that can hold the most amount of apple juice and use the least amount of tin. What shape would you design for your can? Someone said sphere. That's actually the right answer. Sphere is the most efficient solution for maximum juice and minimum tin. Why don't we have spherical apple juice tins? Why? Because they roll off the shelf, right? You can't put them on the shelf. They roll off the shelf, right? So that's not the only reason, but that's one of the reasons why. But that's the optimal solution. It's maybe the best out of the possible solutions, right? That's what I mean by optimal. The fourth type of problem you could encounter is one with no solution, obviously. Now, no solution doesn't mean you can't solve it. It just means it's difficult to verify. So for example, what if I gave you this problem? How many ancestors do you have? It's not like there's no answer to that question. It's just there's no way to verify an answer. It's like an unknown at this point. So there's 4 different ways you can look at problems. By their solution, there's different types, okay? So you dive into a problem and you start solving it, right? So what happens when you solve problems? Well, I would argue that solving problems is the basis of learning, okay? If you already know something and you don't have a problem with it, you're not learning anything. I'd compare this to, say, building muscle, right? If you can lift 20 pounds already, and they say, here's a problem, lift 20 pounds, you're not building anything new. You're just doing something you already know. But if you can't lift 100 pounds and then you start trying, that's a problem that you will build muscle to overcome. So similarly, when you encounter a problem that you can't solve, it will make you learn new techniques in order to solve it. So I would say that solving problems is how we actually learn things. So you do things like you practice things you already know. You engage different areas of your brain, right? You transfer ideas from one side of your brain to another and start doing this. And you get more interested in something as you solve these problems. So I think problem solving is huge. It's a big part of actually learning stuff. But watch out. This will now be transferred to what you do in computer science, where you take your human brain and communicate with a mechanical device, a computing device. In some cases, the computer has the advantage, and in other cases, we have the advantage. So here's what I'd like you guys to do. You weren't that into participating yesterday, but this is really easy. I'm just going to put a sentence up on the screen. Just read it out loud. That's all I'm going to say. Ready? Read this out loud. Okay, for those of you who just said Paris in the spring, you're wrong. It says Paris in the spring. There are two thes there. See? Paris in the spring. Okay? What this is called is an Einstrilling. It is a brain trick, so to speak. The fact is, you had the advantage there. When the computer sees this, it didn't make a mistake. It just went, oh, that's Paris in the spring. Your brain tried to fix it. It went, oh, there shouldn't be a second though. I'll just delete that. And it's Paris in the spring, right? It makes sense. Whether you had the advantage of the computer there is difficult to say, because you made a jump in logic that the computer wouldn't do. Let's try another one. I'm going to put up some columns of words. To start here, I want you to read out loud going down. When you get to the bottom of this one, go up to the top of this one. There's 4 columns. Okay, but what I want you to read out loud is the color of the word. And I want you to go quickly. Ready? Go. All right, very good. What I generally find with this activity is when students do it, generally the fastest column they read is the 4th column. Okay? On the first column, there might have been 1 or 2 mistakes. They might have went white. Oh no, I mean black. I mean, they might have screwed up a word. Second column, maybe less mistakes, and by the 4th column, they've kind of trained their brain to go quicker. Sometimes, I know when I first did this activity, I learned by the 4th column to kind of blur my eyes a little bit, so I wasn't actually reading, just picking up the color. To a computer, it doesn't need to do that. A computer does exactly what you tell it to do. So it has no second thoughts about doing this activity. It does it directly. It doesn't get fooled by anything, is what I'm saying. So in this case, the computer would have the advantage over you. It would go much faster because it doesn't have to blur its eyes, so to speak. All right, let's try one more. You should theoretically it should not be able to read this, but could you please read this out loud? How many people had trouble? A lot of trouble or a little bit? It's amazing how many people have no trouble reading this, and yet this is gibberish up here. If I took this and pasted it into Microsoft Word, you know that little red line that comes underneath it? Like it would be just all red right now, right, for the most part. This is where you have the advantage. You as a human have this ability to do what it says in the article, make quick fixes on words that normally you shouldn't be able to read because you're smart, right? You've got that ability. Your reading skills are at a level where that's really good. So that's good, okay? So in some cases you have the advantage. In some cases the computer has an advantage. But we have to work together to solve problems. So we normally don't do this, but I'm going to break down problem solving into 5 distinctive steps. And here they are, okay? Step 1, what is this problem? We're going to really define exactly what we're solving. Step 2, model it. Now, let's not over-focus on the word model. The word model is a very open word. It depends on the problem. So for example, if it's a math problem, maybe my model is using algebra or using geometry. If it's an essay, maybe my model is like rough copy, final draft kind of thing. If it's, again, my problem is building a fence, maybe my model is using carpentry tools. Like the model depends on the problem. Step 3 would be actually using that model. Once I've decided how I'm going to solve the problem, then I dive in and actually use the technique. 4 would be get the solution. So now I've got my solution. And then 5 would be to check it. Very simple. Some would describe this as a form of the scientific method, but it's basically just step-by-step problem solving. Let's give it a try. Here's a problem. So a salmon swims 3 kilometers upstream, and the current brings her back 2 kilometers each day. How long would it take the salmon to swim 100 kilometers? It's kind of a mathy type question, but let's break it down step by step. So here's the thing. In step 1, this problem is very ambiguous. It's not well defined. So for example, does it mean that the salmon swims 3 kilometers during the day, and then when she goes to bed, the current, like while she's sleeping, pushes her back 2 kilometers? Is that what it means? Or does it mean that the current's so strong that she has to push against it all day long and actually only makes 1 kilometer of headway? And what does day even mean? Does it mean daylight, or does it mean 24 hours? All of these are unanswered questions when I go to solve it. So sometimes that's super important. In step 1, be sure what you're solving. So be clear. So I'm going to redefine it. I'm going to say, okay, how many 24-hour days does it take for a salmon to swim 100 kilometers if in that 24-hour period she swims upstream and then when she rests she's pushed back 2 kilometers? So I've tried to answer the ambiguity there and be a little more clear. Okay, now I need a model. I'm kind of visual. I could do this using algebra if I wanted to, but I think I'm going to sort of draw this out because I like to solve things visually. Okay, so she starts, she swims 3 kilometers, she goes to sleep. The current pushes her while she's asleep. She wakes up 2 kilometers back. So in one day, she started at 0, went to 3, went to sleep, got pushed back to 1. And the next day would go the same way. Swims 3, push back 2. Swims 3, push back 2. Maybe I'll take that and transfer it to something like a chart, okay, or a table. So on day 1, she goes 3 kilometers forward. She reaches the 3 kilometer point. She goes to sleep, gets pushed back 2 kilometers. She wakes up at the 1 kilometer point, etc. If I go through this and I figure out, well, it looks like on day 98 was the day she reached the 100 kilometer point. Now, she went to bed that night and got pushed back to the 98 kilometer point. But the way I defined the question was, on what day would she reach the 100 kilometer point? So I have an answer. I have an answer to the problem. So in step 4 now, because of my model, I've got the answer 98 days. Okay? 98 days based on my step 1. And this is important because in step 1 I defined the problem a certain way. In step 4 I've answered the problem a certain way. If in step 1 I change the way I define the problem, maybe my step 4 would be different as well. And that's really, really important. And then I check it. Now we don't normally always check our problem solving, especially if it's an easy problem. You know, like a little math problem, 2 plus 2, you don't have to necessarily check it. But as the problem gets more complex, like if you're in math class, you might be like, hey, what'd you get on that one? Or, you know, you ask your teacher, what was the answer? Because you want to check it. Okay, depending on it. So checking could be lots of different ways. You could go through it for errors, you could redo it again, etc. Let's try another one. So one day a cab driver picks up 3 couples and takes them to a dance. One girl is dressed in red, one girl in green, and one girl in blue. And then there's 3 boys who are also dressed in 3 different colors, red, green, and blue. So the 3 couples go out dancing. And the boy who's wearing red dances with his little partner over to the girl in green and says to her, hey, Mary, isn't it weird? Not one of us is dancing with a partner dressed in the same color. The problem is, based on this information, sorry, sound effects. What color is the girl in red wearing? Okay, so let's break this down. Step 1, this one's pretty well defined. What color is the partner of the girl in red wearing? There's not a lot of ambiguity here. It's well defined. So I kind of have step 1 done. It's easy. I move on. Step 2, model. Well, I don't know if algebra is going to help me solve this one. I think this is kind of like a logic problem. So for this one, maybe I'll use something like a chart and kind of logically work it out. And I go, okay, what if I say, okay, all the boys here, all the girls here, all the colors laid out, and let's start going through the information. So I do, and I go, okay, well, here's what I know. Red boy is not dancing with green girl, because that's who he talked to while he was dancing with someone. So I know red boy and green girl can't be dancing together. So I'll X that out. Sorry about the sound effects. Here's what else I know. red boy says not one of us is dancing with a partner of the same color. So I know red boy can't be dancing with red girl and blue boy and blue girl, etc. So I can X a few more things out. There we go. Now, what else do I know? Red boy, well, there's nobody else left. So red boy must be dancing with blue girl. We've already X'd out the other two. So that's who I know red boy's dancing with. Blue girl, right here, is already dancing with somebody. So she can't be dancing with green boy. So she can't be. So I'll X that one out. Now I know green girl here has two X's. Green girl must be dancing with blue boy. There's nobody left. And now the rest of the chart starts falling into place. Blue boy is dancing with somebody, so he can't be dancing with red girl. And the final answer comes out. Green boy must be dancing with red girl. Okay, I think I have a solution. That seems to be matches my step one. So let me check it. Again, the checking process might be simple. You could just go, okay, let me just look at that again. Looks good. What did you get on that, right? Now, the thing about checking solutions is it doesn't always totally verify that you got it 100%, because we made a big assumption in this particular problem. I've been to a lot of high school dances in 16 years of teaching, and boys don't always dance with girls, and girls don't always dance with boys. There's nothing wrong with girls dancing with girls and boys dancing with boys. Feel free, boys, to dance with each other right now if the mood strikes you, right? We made that assumption. All right, let's try another one. Last one. How many games are possible in a volleyball playoff when we just have two teams? And if you win two, you're done. Okay? You win the tournament. Huskies and their inevitable rival, the Bunnies. So here's the problem. Who's going to win? How many different ways can this tournament go down? How many different combinations of games? You got to win two to win the tournament. That's assumed in step one. Let's move to step two. Now again, this one I might need something visual. If I think about tournaments, I tend to think of those bracket type things. So I'm going to draw out a tree for this one. I'm going to call it a tree diagram, and here's the way I'm going to draw it. Huskies and Bunnies compete in game one of the tournament. Now one of these two teams is going to win, right? Huskies are going to win, or the Bunnies are going to win. Now we go to game two. If the Huskies won the first game, and then they win the second game, tournament's over. They win both games. But if the Huskies win and then the Bunnies win, we got to go to game three. Okay? Similarly on this side. By game three, the tournament's going to end no matter what, right? Either the Huskies or the Bunnies are going to win game three, and the tournament will end. But the question was, how many different ways can this tournament go? Are you starting to see the answer? Well, here's, for example, the tournament could go like this. It could go Huskies, Huskies, or it could go Huskies, Bunnies, Huskies. So as you follow through the tree, the answer I see is 6. There appears to be 6 different ways this tournament could go. Okay? Whoops. So I'm going to answer 6. That's going to be my solution. Okay? In checking it, sometimes the way we solve problems is we actually do it a different way. So maybe I'm not going to use a tree this time. Maybe I'm just going to write them out. Write out the possibilities. Here they are. Huskies, 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 Bunnies, Huskies, etc. That checks it for me. Yeah, there's 6 different ways to do this tournament. So it's a very general, and I'm not here to teach you about tournaments. I'm not here to teach you about salmon or dancing. God help you if I was. I'm here to talk about problem solving, slowing yourself down, and solving problems systematically. Okay, but we'll pick up on this tomorrow. Didn't realize the time was going the way it was going. Okay, so another tool that we can use to help with our problem solving is this power of analogy that we have. We as humans have this power, and the computer really doesn't. Analogy is this ability to draw on our wealth of experience and our sort of personal history to make predictions and to make jumps in logic. So let's try an example. What if I told you Sue is a good basketball player? Sue is 6'2", tall, slim. The question that I want you to predict is, do you think Sue will be a good gymnast? Well, at this point you may have trouble predicting yes. You might say, well, I get she's good at basketball, so she's probably athletic. She seems tall and slim and 6'2", so I don't know. It's hard to tell. But what if I added more information? Would that change your prediction? So I'd say, okay, Sue's very best friend and they do everything together, is Ingrid. She's 6'2", also tall, also slim, also a good basketball player, and also a good gymnast. Now again, it's a prediction. We could be right, we could be wrong, but using the power of analogy, we might be more inclined now to say, yeah, I think Sue, might be a good gymnast. By adding that little bit more information, we're drawing on our experience and seeing if we can use this. But analogy, we use this to observe similarities and make a conclusion. Maybe we do conclude that Sue will be a good gymnast. But analogy is not perfect. And for the computer, it's even less so because there's less to draw from. What if I added a little more information? What if I told you that although Sue, the one that we're predicting if she's a good gymnast, is in fact a good basketball player, but she actually plays wheelchair basketball? This new piece of information might let you draw from your analogy and say, you know what? If she's in a wheelchair, she may have some sort of a paralysis, and if that's the case, I don't know if being a gymnast would be something that she would be capable of. So at this point, your prediction might be to say, no, I don't think she is a good gymnast. And this is, again, a prediction based on using analogy as your model, okay? It might change, and it might change the way you make your decisions, okay? But this power of analogy is something that we as humans have and we can draw from. And it's really not something the computer can draw from. So it's important for you to remember that when you're programming, you're going to be communicating with a device that doesn't have the same sort of thinking patterns that you do. Okay, so let's wrap it up. When you go through the 5 steps and you start at step 1, what is the problem? You're determining what you're trying to find. What do you know? What are you given in terms of information? You might want to restate it to kind of make it more clear. What information is not given that you need to add in there? Maybe clear up anything that's vague and interpret the way it's worded. And basically in step 1, get the problem to a state where you have a definite path for solution in front of you. Then you go to step 2 and you get a model together. Now a model depends on the problem, right? Sometimes you need pencils, sometimes you need hammers and nails, sometimes you draw out diagrams, sometimes you create charts, sometimes you use formulas. It depends on the problem, what sort of model that you're going to put forward, right? So a model is a very loose term that sort of builds from your tools to try and solve the problem. So in step 2, you figure out what model you need, and then in step 3, you start filling out the model. You start actually putting the things in place, putting numbers into the formula, using the tools. And this can also mean things like trial and error, leaving the problem for a while and coming back to it, solving a slightly simpler problem, and then going back to the original problem to see if you can figure it out. This is the step that you spend the most time in. Once you've determined what the problem is, figured out what your model is going to be for solving it, then the actual solving it in step 3 is where you spend the majority of your time. So then you get to step 4. Now you have a solution. You've figured it out, you've gone through your model, and you have a solution in place. And then finally in step 5, you check it over. Is this a reasonable thing? Should I do it again? Should I ask others to see if they got the same solution? These are the 5 steps of problem solving that are used to come up with answers to various problems.